Can everybody hear me?
Yes, it sounds great.
Yes, we can hear you. We can hear you.
Okay, great. Thank you, Joe, for that introduction, and thank you, all of you, for inviting me to this meeting, which is the part that I've heard has been very educational for me. I wanted to talk today about the subject that has interested me for, well, since the pandemic began. When the pandemic began, we all kind of isolated ourselves and searched around for interesting things to do, things that would stimulate us. And I turned to Mathematica and a subject that I'd taught many times at Stanford, Fourier transforms, and included in that some aspects of Fourier optics. So I'd like to talk today about using Mathematica to illustrate both Fourier transforms and Fourier optics. So let me move to a few bullets here. Of course, many laboratories are closed now, and access to experimental facilities is somewhat limited, and classrooms are in most places unoccupied due to limitations on crowd gathering, and so classroom lab demonstrations are gone. And in the absence of these laboratories, what do we do? Well, I think simulation can be a tool that helps us a great deal. Home computers are fast enough so that we have rapid tools for teaching and research. And if we can incorporate dynamic illustrations, changeable by the reader, then I think some interesting and unique things can be realized. So what language you use depends on your preferences. MATLAB is more popular with students. Mathematica is more popular with me. And I have used Mathematica quite a bit for illustrations in other books in the past. It's for me to immerse myself in Mathematica and to use some of the lecture notes that I had gathered from my many times teaching Fourier transforms. I like Mathematica because it's such a seamless, it has such a seamless ability to mingle continuous and discrete math. And I'm going to illustrate in this talk, first of all, some dynamic figures having to do with the theory of Fourier transforms, and then I'm going to illustrate with some dynamic illustrations drawn from the field of Fourier optics. I've hidden the code in everything that follows, so my emphasis is on the figures themselves. And this document you're looking at is a Mathematica notebook, in fact, and it can be read with either the full Mathematica program or the free software Wolfram Player that can be downloaded from the Wolfram website. So my first illustration is for the concept of convolution. Convolution, of course, arises in many different scenarios. We find them in linear systems analysis, whether it be time functions or space functions in optics. I'm illustrating here with a one-dimensional example. I would like to convolve this right triangle function with this Gaussian function. And the convolution integral, as defined, is this right triangle function reversed, since we have a minus sign here, and shifted by x times the Gaussian function. And we integrate that product over infinite limits. So let's see what the integrand looks like here, the product of the right triangle function shifting and the Gaussian function. So here we have the right triangle function has been reversed, so it's now a left triangle function, and we're going to gradually slide it across this Gaussian function, and the green area, which you see underneath, is the product of these two functions. The green area is the area of the green area is in fact the convolution integral at this particular displacement. So there we have a dynamic figure that shows what happens when we slide those two functions past one another. And this is the end result as a function of x. You can see the peak is actually a bit to the right of the vertical axis here. So that's one illustration that is interesting. And then there's another theorem I'd like to illustrate, which is called the modulation theorem of Fourier transforms. So to set that up, let's imagine that we have a function g of x. X could be time or it could be one-dimensional space. And it has a Fourier transform, this capital G, of a frequency variable, u. And the modulation theorem states that the Fourier transform of our function g of x multiplied by cosine 2 pi times a frequency, cyclic frequency nu times x, is 1/2 of g of u shifted by nu plus 1/2 of g, capital G, shifted by minus nu, where nu is the frequency variable of the cosine. So to illustrate, let's let g of x be a rectangle function. That is value 1 on minus 1/2 to 1/2. There it is, minus 1/2 to 1/2, height 1, and 0 everywhere else. That function has a Fourier transform, capital G of u, which is a sine pi u over pi u function, so-called sinc function. And that function is illustrated here as a function of the frequency variable u. So how does this spectrum change as we change the frequency variable of the cosine? This is what the modulation theorem is all about. And so we're going to see what happens. Here I have a dynamic plot. This bar will let me adjust the frequency of the cosine. And we'll see what happens as we increase that frequency. Right now, the frequency is 0, so I have just a rectangle function. And we see that the spectrum is the sinc function, just as we had before. But now I'm going to increase the frequency to 0.5. Sinc function is beginning to drop and change its shape somewhat. Change it to frequency 1, and you can see two humps are developing around the origin. Here we go, 1.5. Here we go, 2. Here we go, 2.5. Here we go, 3. 3.5. 4. 4.5. 5. And you see what has developed is we have now two sinc functions, one displaced to the center frequency of the cosine and the other displaced to minus the center frequency of the cosine. And the height of these sinc functions has dropped to 1/2. So that is the modulation theorem. The sinc function breaks up into two sinc functions displaced in a manner determined by the frequency of the cosine. One more illustration from the Fourier transform area. I'd like to illustrate the sampling theorem and aliasing. So we're going to start now with a function of x, that is time or possibly space, which is the square of a sinc function. Here's that function down here. You can see the square sinc function. And the Fourier transform of that function turns out to be a triangle function, a symmetric triangle function, as shown here, capital G of u versus u. Height is 1, drops to 0, 1, and minus 1. I've illustrated over here, let's say in the time domain, a few sampling points, possible sampling points, represented by these little dark circles. And those sampling points are separated by a distance that I will call x. That's the sampling interval. So the bandwidth of this function the triangle function in the frequency domain is 2 units, -1 to 1, whatever those units represent. If I sample g of x with sample spacing x, whatever x may be, the sample spectrum, which I'll call g hat of frequency variable u, it's an infinite replication of triangle functions with spacing delta nu between those replicas, given by the reciprocal of the sample spacing. That is, the separation of these triangle functions is 1 over the sampling interval. To recover the original signal from the sample spectrum, we must use a rectangular filter passband that selects the spectral island that's centered around 0 frequency. And in this example, because the bandwidth here is 2, the sample spacing 0.5 or 1/2 is a critical sampling spacing, and undersampling occurs when the sample spacing in the X domain is greater than 0.5, whereas oversampling when the spacing is smaller than 0.5. So here we have an illustration, and I'm going to start actually with the sample spacing being 1 unit in the X domain. With 1 unit in the X domain, we have total overlap of all these replicated triangle functions, and they overlap in such a way that they create just a flat spectrum. That flat spectrum is filtered by this rectangular passband filter and produces a sinc function, because the Fourier transform of the rectangle function is a sinc function. This is for sample spacing 1. But now let's suppose I decrease the sample spacing gradually. You can see the peaks of the triangle functions beginning to appear. And I keep decreasing the sample spacing, and you see the overlapping triangular spectral islands. And a rectangular filter is picking out the central island here, but it's not a full triangle function. It's got this baseline here because of the overlap of these triangle functions. So we'll keep decreasing the sample spacing until we reach 0.5. And we reach 0.5, for the first time, this rectangular filter is able to sift out the triangle function, and as a consequence, it's able to change this sinc function gradually to a sinc squared function, which is the function we started with. And that happens at 0.5. And as we lower the sample spacing further and further, the spectral islands move further and further apart, and we continue then to have proper sampling of the sinc squared function, and the central island of the spectrum is being filtered out under all of these conditions. So that's an illustration of the sampling theorem, and of course, when these spectra overlap, this is what is called aliasing, and it will cause a distortion of the recovered function. See, what am I at? I'm at 0.6, so let's decrease to, that went too far. I go to 0.6. So here you can see that aliasing is starting to set in and becomes worse and worse as I spread the samples further and further apart. So that's an illustration of the sampling theorem and aliasing. Now I'd like to turn to Fourier optics. And I'm going to consider first Fresnel diffraction by various kinds of apertures. So the Fresnel diffraction integral in 1 and 2 dimensions, the complex amplitude of the field we observe generated by an aperture with an amplitude transmittance G at a distance Z with wavelength lambda is given by this one-dimensional infinite integral, which, by the way, is a Fourier transform of the product of G and the quadratic phase function scaled by this 1 over lambda Z. By the same token, the two-dimensional Fresnel transform, or Fresnel diffraction pattern, is two-dimensional integral. This integral sign came out a little bit too short. This is the aperture function, amplitude transmittance of the aperture, a two-dimensional quadratic phase vector, and then a two-dimensional Fourier transform, a pair of infinite integrals. Of course, the diffraction patterns that we detect are the squared modulus of these diffracted fields, the intensities of those fields. So let's do a simple case. First, we'll look at the Fresnel diffraction by a one-dimensional aperture of fixed width 1, a rectangular aperture, and we'll look at various values of lambda Z. As I change lambda Z, you can think of lambdas being fixed in Z as increasing or decreasing, as the case may be. So we start out with this aperture. And here we are at a product of lambda and Z equal 0.001. Now we're pretty close to the aperture. And you can see that the diffraction pattern is kind of hugging the aperture. We have this Gibbs phenomenon, if you like, that consists of ringing. And we have a little bit of overshoot here at the edge. But now what happens when we start to increase the distance further and further? Well, here we've increased it to 0.1. And here is the Fresnel diffraction pattern for that product of lambda and Z. Here we increase it to 0.2. Here we increase it to 0.3. Here we increase it to 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Excuse me. And as you might expect, as the distance gets larger and larger, or the product of lambda and Z gets larger and larger, we are transitioning from Fresnel diffraction to Fraunhofer diffraction. And the diffraction pattern is looking more and more like sinc squared. Since the Fourier transform of the rectangle is a sinc function, the corresponding intensity is a sinc squared. So here is a sinc squared function we're approaching, and as you can see, as the distance gets larger and larger, the diffraction pattern, the Fraunhofer diffraction pattern, is getting wider and wider. So that's the case of a rectangular aperture function. Excuse me. Let's look now, again with a 1D example, at a half-plane opaque screen with a transmittance of 1 to the right of the origin and a transmittance of 0 to the left. I should have mentioned right at the beginning that our Fresnel diffraction formulas are scalar approximations to what's really happening, and they should be pretty accurate, provided we are viewing the diffraction pattern at distances that are many times lambda. So here's the aperture function, 1 to the right, 0 to the left. And here's lambda Z. I'm going to show you the values here. This is 0.1 for lambda Z. Let me increase now to 0.5. And you can see that the diffraction pattern is widening and pulling away from the origin. But one thing I'd like to point out is that in every case, this diffraction pattern is crossing the vertical axis at 0.25. That is at 1/4 the height of the opaque half screen. that we used. And this is characteristic of coherent imaging of an edge. With incoherent imaging, it crosses at 0.5, and the ringing is absent. But with coherent imaging, it crosses at 1/4 of the height of the edge, and it has a good deal of ringing. This spreads as we move away further and just heading into the Fraunhofer region. Another example, 1D diffraction by a 180-degree phase step at the origin. So let's say to the left of the origin, we have 0 degrees phase shift. To the right of the origin, we have 180-degree phase shift, and there's no attenuation at all in its aperture. So let me go back here to 0. This is lambda z, and let me show the value, 0.1. We increase, and the diffraction pattern pulls away from the origin and heads towards a Fraunhofer diffraction pattern. And just a comment about the fact that we always have 0 intensity at the origin. And this is because the Fourier transform of this product of the phase aperture and the quadratic phase function has opposite signs to the left and the right of the origin, and they cancel out right at the origin in the diffraction pattern. So we always have 0 at the origin. One more example. This is a 2-dimensional example, and the aperture function I've chosen is g of x and y is a 0-order Bessel function of the first kind that's radially symmetric. Depends on the square root of x squared plus y squared. Now, you could, of course, object that this function, as defined, is infinite in extent, and undoubtedly we have a finite pupil. Well, let's just suppose that that finite pupil encompasses most of the Bessel function where it has significant energy, and then we'll talk about what happens due to the aperture function in a minute. So here is our diffraction pattern when lambda z is 0.1. And now I'm going to increase it, and there's a bit of computation that has to go on. There it is. Hasn't changed much. There it is. Hasn't changed much. There it is. And let me advance all the way to lambda z equals 10, and it hasn't changed. Well, this is an interesting aperture distribution that is a non-diffracting aperture. This aperture function produces a diffracted field that does not spread. And so it's sometimes called a non-diffracting aperture. Of course, if we now bound it by a finite pupil, this property is going to be ultimately destroyed. But the more of the Bessel function that's contained in that finite pupil, the further away from the diffracting aperture we can move without much change in the diffraction pattern. So that is another interesting example of diffraction. Now I'm moving to another subject. And this is the problem of imaging a pure phase object. And just for simplicity, I'm going to assume this 4F imaging system. Object, focal plane where we have the Fourier transform, and another Fourier transform to produce the image. And the problem I'd like to pose is, how can we make a pure phase object in the object plane visible in the image plane? And we're going to consider several methods. First, I've got to define a phase profile. And here I've defined a phase profile consisting of several circularly symmetric pyramids with different base sizes and heights equal to pi/4 phase shift. If I make a density image of this phase profile, I get something that looks like this. If we have an imaging system that somehow is able to accurately show us in its intensity what the phase is at each point in the object, we should see an image like this. This would be an ideal image that we would obtain if we can. So we create a phase object by taking the exponential of I times the phase profile we've defined. And if we don't modify the focal plane amplitude distribution, then the image of this object, since it's only phase variations, will have no intensity variations. So we won't be able to see the phase objects. So now we're going to try several methods to view the phase. And the first thing that might come to mind is, well, let's put an aperture in the focal plane to cut down on the amount or the number of Fourier components that are passed. And if we take this phase object and cut off part of its spectrum, perhaps it will become somewhat visible. So here in these examples, I have an aperture that's 1/8 of its full size. If it were its full size, we would see nothing. The image, although you may not think so, because you see this brightest image in the same place you saw the brightest, the most intense phase distribution. But as it turns out, by eliminating some of the components of the phase objects, we've caused some image intensity to appear. And the image is inverted, actually. It doesn't look anything like the phase profile. The brightest dot actually comes from the smallest phase pyramid in this inverted image, because the spectrum of the smallest phase pyramid is the widest, and it's been most affected by the focal plane stop. The largest phase pyramid, which I think is right here, is almost invisible. Its effect is almost invisible, since its spectrum has been the least affected by the stop, and it remains primarily a phase image. That's because its spectrum is much narrower, and the stop around the aperture in the focal plane, has not affected it that much. So anyway, we have not succeeded in getting a very good picture of the phase object. So now we're going to try something different. We're going to eliminate the focal plane restriction. We're going to open up the focal plane completely, and we're going to put a small absorbing dot with 1 pixel radius on the optical axis in the focal plane. And by doing that, we will block the zero frequency component of the object. So here's the phase object itself. If the phase is small, which it is reasonably small in this example, and we block the zero frequency component, then the intensity that we'll see will be proportional to the phase squared. And here we see the inverted image of such an object, or such a case when the focal plane stop is right on the optical axis and is 1 pixel wide. And what we're seeing is a square of the phase profile, not the phase profile itself. It's not a very good replication of the phase because it represents the square of the phase. So maybe we can do better. So now we're going to try Zernike phase contrast, which Fritz Zernike received a Nobel Prize for in physics in 1935. And rather than putting a small absorbing dot on the optical axis, I'm going to put a small phase shifting dot on the optical axis in the focal plane. And that dot has a phase shift of pi/2. Now I view the resulting image with the focal aperture completely got a dynamic here, completely open. Wow, that was a good attempt, but let's move on. Here we have, again, for small phase shift, 1 plus the imaginary constant times phi. But when I shift the phase of the on-axis light by pi over 2, what I have accomplished is that I now have the squared magnitude for intensity of 1 plus phi, which is approximately 1 plus 2 phi. So there's a background, and I have twice the phase, not the phase squared, but the phase. Now in this picture, the background, because it's a density plot, the background has kind of been suppressed to dark, and we see the 2 phi here in the image. And this, if you recall the original phase object, is a very good rendition of the original phase object. So the Zernike phase contrast has given us the opportunity to see this phase profile and with much more fidelity. Now, an interesting question to ask is, what happens if I open that 1 pixel diameter phase shifting dot? What if I make it bigger? In other words, 2, 3, 4 pixels. Right now, the radius of that dot is 0.5. And we see a nice representation of this. You see it's riding on a background of 1.0, and then we see a nice representation of these 3 pyramids representing intensity. And now I'm going to start to increase the dot. There's a little computation that's got to go on here. Increase it a bit more. 1.5 radius, so 3 diameter. 4 diameter. You see there's beginning to be a depression around the big pyramid. And that gets pretty bad if we go all the way to the end here and look at, you can see that the big pyramid has kind of disappeared. And that's for a radius of 6 pixels for the phase shifting dot. So what's the explanation for these image defects when the dot gets larger and larger? Why is the largest phase pyramid affected the most? Well, the answer is the larger the pyramid, the more concentrated its spectrum is around the origin. Thus, the more of its spectrum is affected by the phase shifting dot on the axis, which is an unwanted effect. If the phase shifting dot is too large, spectral components near the origin are no longer in phase with the on-axis light. And this destroys the ability of the phase contrast process to show the phase. So this will happen as we open the dot up bigger and bigger to the other. It will happen also to the other pyramids. Okay, the last topic I want to discuss, and I've run past my half-hour stated intention. Is it okay if I continue?
Yeah, no problem. No problem.
Okay. So I want to illustrate the simulation of speckle in coherent imaging systems. And again, I'm assuming a 4F imaging system. But this time I'm going to construct first an object transparency that has some structure, sandwiched with a pure phase diffuser. And this could be a representation, for example, of imaging a rough object in reflection. The phase roughness is several times 2 pi radians, and the object structure consists of 3 inverted circularly symmetric periods. So here is the object that I've assumed before I've introduced the diffuser. And you can see the inverted pyramids with different base sizes. Now I'm going to introduce a diffuser. And what I'd like to do is to vary the diameter of the focal plane aperture. That is, I'm going to introduce an aperture in the focal plane. The parameter S is the fraction of the pupil that I leave open as I close down the aperture in the focal plane. And here I have the aperture including the entire focal plane. And what I see is these three, I see in a density plot, these three inverted pyramids. I don't see any speckle at all, and that's because when the aperture is fully open, I'm resolving my assumed diffuser phases so that they don't show up in the image. They're pure phase in the image, and they simply don't show up in the image intensity. So I've resolved the roughness, if you like. But now I'm going to start to increase I'm going to start to decrease the aperture size in the focal plane, and there's little computing goes on here. And now you're beginning to see some speckle appear. Here, the aperture diameter is 8/10 of the full pupil. And here, little computation, 6/10. Speckle's getting more noticeable. Here we're down to 4/10. And it's getting more and more difficult to see the edges of these depressions. And now it's getting almost impossible. This is 0.2 diameter, now 0.01, and once this is finished calculating, all we'll see, or maybe it's finished now, all we see is speckle. We don't see the inverted pyramids at all. And here's another view, which is a different kind of representation. I'm reducing the size of the pupil. Speckle is appearing. Speckle's appearing. If I move this so that I look down on it, you can see the three indentations. And let me just jump to the worst case. Basically, the pupil is so small now that there's almost no light getting through. So in any case, when the pupil is fully open, we see no speckle. The images of the depression are quite clear. The phase structure produced by the rough surface or the diffuser has been fully resolved by the optical system. And as we stop down, line speckle begins to appear. As we stop the pupil down further, the speckle gets coarser, and the determination of the boundary of the object depressions is much harder. And if it gets coarse enough, the pupil small enough, we can't really see them at all. And now I want to do a little bit of shameless advertising. The SPIE will next month be publishing a book entitled Fourier Transforms Using Mathematica, which includes a lot of properties of Fourier transforms. It's an attempt to teach both Fourier transforms and Mathematica hand in hand. And it includes chapters on digital image processing and coherent optics, and as well as many chapters on the properties of Fourier transforms and transforms related to Fourier transforms. So with that closing, I'd like to say thank you all for listening, and I wish that all of you stay healthy. Thank you very much for your attention.
Thank you, Joe. This is great. I'm going to open it up and see if there are some questions or discussion that people want to have. We'll have to toggle your mute on and off, but I think we can handle that. If you...
I have one question. It's Randy.
Okay, go ahead.
So my question is, you talked about the non-diffracting beam. Can you talk about practical ways of producing that? Oh, you need to unmute.
Unmute me. Okay, I'm unmuted. Well, in practice, I think you would have to have a finite pupil. So it would be non-diffracting over a certain distance. And beyond that distance, it would start to diffract like any other function. So it's not really possible to build up a scheme to make this particular vessel function a non-diffracting beam forever, speaking practically.
Good point. Other comments or questions?
I have another question. I'm definitely going to load Mathematica on my machine because these are excellent demonstrations for classes and for students and talks. Is your book going to talk about holography at all? The what happens when you do coherent detection of images? You're still no.
Yes, yes. There is a section on what people these days call phase shifting holography. That is holography with an on-axis reference beam that is phase shifted several times, combining those interference patterns to form a hologram, basically. So there's a section on that. Off-axis holography is not discussed in there, but on-axis holography is. And I just want to mention that the SBIE, when it provides this book, which is generated from a PDF file, you will also get about 120 megabyte Mathematica file that has all of the dynamic figures. The PDF printed book, there's no way to have dynamic figures, but the software that comes with it, you can have all the dynamic figures that are in the book, and that is supplied along with the book. And again, I'm going to mention that Wolfram Player allows you to see all the dynamic figures. You just can't change the file and experiment with apertures of your choice. You have to live with what's there, but you can see the dynamic figures change. And that's a free software download.
Other comments or questions? Oh, there is one in the chat, and I'll either let Slater ask it out loud, or I'll just ask it for him. But you're welcome to join in, Slater, if you want. But he asks Joe, what would be an example of a scene or an object that would produce the phase shift cones in the diagrams?
Okay. Well, these were totally synthetic objects that were designed just to illustrate some points, and I wouldn't in any way claim that they represent some particular object. I mean, maybe they do, but that wasn't my intention to illustrate with a real object. There, in this book, there are some examples. This is a digital image processing example in which a real image has been filtered with a Sobel edge detector. It's an image of a dragon face. So in the book there are maybe some real images, but not in what I've shown you today.
Okay, good. And Slater explained that he has no mic right now, so that works fine. If people want to put questions in the chat, it works great. He says, thank you, Joe, for your response. So any others? So Joe, how many more books do you think you'll write in your career? I'm impressed that you're still writing books. This is great.
Mute. Well, I can tell you that I have I have written the last edition of the Fourier Optics book, the 4th edition that's available. I'm not going to write another edition of that. Excuse me. And I've written the last edition of the statistical optics book. Is that the 2nd edition? I think. And I've written the last edition of my speckle book. That's the 2nd edition. So this book would be very easy to expand, and maybe I have the energy to do that. I've actually been working on another potential book that is a book more purely on Fourier optics using Mathematica, without all the background in Fourier transforms. And I don't know whether that'll ever be completed, but that's what keeps my mind occupied these days. It's always good to have your mind occupied.
I agree. That sounds really great. It's impressive. You've used your pandemic time better than many of us. Any other questions or comments? Last call here. Okay, well, I want to thank everybody for being here. I'm going to put on my Halloween hat so that we can have some Halloween fun. And then if Dr. Goodman had been able to come in person, I would now present him with a copy of my book, which I guess isn't showing up very well in my screen, but it's called Optics in the Air. It's published by SPIE also. And it's a book about halos and rainbows and things like that. And I'll be happy to sign this and mail it to you, Joe, in gratitude, just a small token of gratitude for you speaking to us today. And when you come to visit us in person, maybe we can have some more fun. So I know I expressed the sentiments of everybody in thanking you for joining us. And we hope that you and your wife and all your family stay healthy. And thank you, everybody, for being here today. There's different messages coming in on chat, if you can see those. Different people saying thank you in various ways. Take off my silly hat. Okay, so that concludes the conference. Michelle, thank you so much for your guidance and assistance all day. Joe Goodman, thank you so much for being with us today. It's been a pleasure to have you here. And all the speakers and all the attendees, I express my gratitude to you and well wishes. And maybe next year we'll be back in the beautiful new building that we built and aren't seeing much of these days. So with that, we'll sign off. Thank you very much.